Welcome back. My name is Rui Hugman. This is the second of two videos prepared for the groundwater modeling topic of the groundwater hydrology degree at Flinders University. In the previous video, we covered groundwater model history matching and calibration. In this video, we will address uncertainty analysis. As these topics are quite vast, condensing all of the necessary information into a couple of hours is quite challenging. Rather, what these two videos aim to do is provide a broad overview of concepts as a primer. And then throughout the video, I'll provide links to other videos and documents which delve into the concepts in a lot more depth and rigor. The end goal is to provide you with the core concepts that you will require in order to apply uncertainty analysis tools when undertaking groundwater modeling in practice. And to this end, the video is accompanied by a series of tutorials which take you step by step through the process of applying these concepts in practice using tools available in the PEST suite of software. So to make full use of this video, you should complete these tutorials. Before we get started, the material covered in this video assumes that you've watched and/or read a couple of things beforehand. Firstly, I assume you've watched the first lecture, which gave an overview of history matching and calibration. Even better if you have taken the time to watch some of the other videos and material linked to during that lecture. Secondly, after the lecture, you should have undertaken the tutorial on model calibration, available from the GMDSI website. This would have provided you with a bit more understanding of how all of the concepts we discussed are applied in practice using PEST, as well, of course, as introducing you to working with PEST. Once you've done those two, you should have a grasp of both some of the theory as well as the practicalities of history matching and calibration. And as we keep repeating, those are merely a step along the way towards accomplishing the goal of decision support modeling, making a prediction, and quantifying the associated uncertainty. Before watching the current video, you should watch the GMDSI webinar on Uncertainty 101. It's a talk given by John Doherty and Catherine Moore, which provides an excellent overview of the concepts underpinning uncertainty analysis in groundwater modeling, as well as the general approaches which we adopt in practice. That webinar doesn't go into too much math or technical details, so it's always a good place to start. Their presentation is about 40 minutes long, with some bonus Q&A at the end. If you haven't watched it yet, please go and do so now, and then come back to this video. Here we are going to dive into a bit more technical detail of how to actually implement uncertainty analysis. We'll start off with linear analysis methods, taking you through some of the underlying theory, and then a quick overview of how to actually apply them in practice using the software available as part of the PEST suite. We will then provide an overview of nonlinear analysis methods, some of the benefits and drawbacks, as well as commonly used methods and techniques. You should complement this video by completing the tutorials on the GMDSI website. They should help you to better understand how to actually translate these concepts into practice, as well as giving you a bit more familiarity with PEST and PEST++ families of software. Secondly, the presentation in this video is heavily based on the PEST roadmaps, which are a set of slides and short documents available on the GMDSI website. They are often quite useful to get a quick introduction to a specific topic or concept. It's always a useful resource to have at hand. Lastly, there are two additional videos which may be useful to complement this lecture. These are the two webinars on decision support technology. Both Part 1 and Part 2 cover linear and nonlinear uncertainty quantification tools. They cover the same topics as we're going to be talking about here, but with a lot more rigor and a bit more depth. So if you wish to expand your knowledge on these concepts, then I do suggest you go and watch them. Just a quick recap before we get started. So our goal when modeling is to make a prediction of the impact of some management decision on some decision-critical outcome. Decision makers will usually want to know whether if they implement a planned action, then will some bad thing happen? Modeling aims to answer this. As we have seen, as groundwater systems are extremely complex, extremely heterogeneous, and the data that we have available to characterize them is often sparse and inherently uncertain, any prediction made by a groundwater model is accompanied by uncertainty, usually a lot of uncertainty. So any model prediction must include a quantification of the associated uncertainty. Quantitative estimates of prediction uncertainties are usually expressed as a mean value, so that blue line shown in the figure, with the associated variance or standard deviation, or even alternatively as a range for a given confidence level. So that would be the standard deviation of that statistical distribution, illustrated by the probability distribution here, or the range being how far apart that could be at a 95% confidence interval, for example. So the uncertainty of a prediction comes from several sources. Some of this uncertainty we cannot reduce. This type of uncertainty is referred to as intrinsic or aleatoric uncertainty. It comes from the variability of things that we cannot reduce by collecting more data or knowledge on the system. It includes things such as measurement errors, so how wrong our field measurements of state or system properties may be, as well as things such as future climate or human behavior, which we do not really know what they will be. These are all things that we can at best describe probabilistically and cannot reduce by collecting more information. On the other side, we have epistemic uncertainty which can be reduced by acquiring new knowledge. In this camp, we include our model parameters, the values of which can be informed by history matching our model against real-world observation data. Now recall that parameters are not restricted to things such as hydraulic properties. Parameters can be pretty much any kind of input into a model. So hydraulic properties, boundary condition values, even things such as pumping rates and so on, all of these are parameters. Through history matching, we reduce the range of possible combinations of model parameters to those which can replicate system behavior to a level which we consider adequate. Of course, given that our field data is also uncertain, that uncertainty propagates and affects our model's uncertainty. Added to this, as we have said, as observations are much fewer than the amount of parameters in our model, the uncertainty of many of the parameter combinations will likely also not be reducible. These parameter combinations are said to reside in the null space. So uncertainty quantification methods aim to account for these various sources of uncertainty and how they translate to the uncertainty of a model prediction. In essence, or at least conceptually, these methods identify sets of parameters which can explain field data, accounting for the error in field measurements, of course, and the sample of predictions from these sets of parameters describes the statistical distribution of possible predictions or possible outcomes. The methods we will discuss differ in how they identify those parameter sets. Linear analysis methods, for example, use statistical concepts to estimate the propagation of observation and parameter uncertainty to that of a model prediction. You may also have heard of Monte Carlo methods. These are conceptually quite simple and essentially work on the idea of randomly sampling parameter values a couple of hundreds of or thousands of times, running a model with each of those sets of parameters and thus coming up with a sample of predictions. This sample may be conditioned by throwing out model runs which do not represent the past well, which is called rejection sampling. Although this is conceptually simple and is a good embodiment of Bayes' theorem, these methods are not very efficient and are superseded by other more sophisticated approaches. You may also hear about something called the null space Monte Carlo method, which is a more efficient method of sampling parameters which are almost calibrated. Until recently, this was a common method for nonlinear uncertainty analysis. Now, and although it is still a useful option in some cases, in practice, it has essentially been superseded by more recent methods embodied in ensemble methods. As we'll see later, ensemble methods provide a computationally very efficient way to sample both the prior and the posterior probability distributions, whilst also accounting for measurement error. At the time of recording, ensemble methods are probably the most easy to apply and pragmatic tool for nonlinear uncertainty analysis and groundwater modeling. Linear uncertainty analysis, which is also known as first-order second moment analysis, provides an approximate mathematical characterization of prior predictive probability distribution and of posterior parameter and predictive probability distributions. It has other uses as well. It can be used to demonstrate how the history matching process bestows worth on data. It can also be employed to track the flow of information from field measurements of system state to parameters, and ultimately from parameters to model predictions. So it's an efficient tool to determine which parameters are being informed by history matching and which observations are informing those parameters and ultimately informing the prediction. The outcomes of linear analysis are approximate. This is because, as we saw in the previous video, the relationships between changes in model outputs and changes in model parameters are not actually linear. But linear analysis relies on the idea that they are. Although in practice they aren't, the approximations that we can achieve through linear analysis are often good enough to be useful for decision making. And perhaps just as importantly, these methods often provide extremely useful qualitative aspects to a modeling analysis, providing insights into the nature of a model's uncertainty, as well as previously mentioned, the ability to track the flow of information from data to parameters and from parameters to prediction. A major advantage of these methods is that they are computationally frugal, because all that they require in terms of model runs are the calculation of parameter sensitivities. Recall that where calibration is undertaken using software such as PEST, as part of that process, a Jacobian matrix is filled. Elements of this matrix are the differences in each model output caused by a change in each model parameter, also known as sensitivity coefficients. These are the parameter sensitivities which link changes in parameter values to changes in observation values. If a model has been calibrated, then by default a sensitivity matrix will already be available. If a model is not calibrated, at worst, to fill the matrix, the model must be run as many times as there are adjustable parameters. There is an important detail in that this matrix must also include sensitivities for the prediction or forecast of interest if predictive uncertainty is being assessed, which is usually the point. What this means is that the model prediction must be included as an observation in the model run whilst generating whilst filling the Jacobian matrix. Now, it's often the case that the model being used for calibration is not quite the same as the one being used for a prediction, especially if simulating the prediction significantly increases model runtime. In such cases, even if calibration has been undertaken already, sensitivities will need to be recalculated with the prediction included in the model run. In practice, this means rerunning the model as many times as you have parameters, but with the predictive model rather than the calibration model. Along with sensitivities, these methods require a modeler to provide an assessment of the prior parameter probabilities, as well as the observation uncertainty. Both observation and parameter uncertainties are expressed through covariance matrices. These are matrices whose diagonal elements contain the variance of each observation or parameter. The off-diagonal elements contain the covariance between combinations of parameters of observations and or parameters. PEST and PyEmu have a series of utilities and functions which facilitate the construction of these matrices. It is not as complicated as it might sound. In practice, what is required from a modeler is to specify a variance for each observation or parameter, and where parameters are correlated, assigning covariances between pairs of parameters. The latter is also accomplished with various tools available in the PEST and PyEmu suites of software. In practice, observation uncertainty is expressed by setting observation weights to equal the expected observation error. This error reflects both the precision of our ability to measure the observation in the field, as well as the ability of the model to simulate it. These do not have to be the same weights we assign during calibration. Usually in practice, they are adjusted, accounting for the level of fit which was achieved with the calibrated parameter sets, with weights assigned as the inverse of the standard deviation of the misfit or the error. Again, PEST and PyEmu have utilities and functions that can undertake this for us. And again, in practice, observation uncertainties are usually assumed to be independent, so without covariance between noise or uncertainty at different observations. Prior parameter uncertainties express our expert knowledge of the system, translated as the possible range of parameter variability which may occur at a given site, as well as the correlation between them if it exists. The latter is often formalized using variograms for spatially or temporally distributed parameters in order to express the propensity for parameters which are closer together to be more similar. Again, utility software and functions from the PEST and PyEmu suites undertake this for us in practice. The GMDSI tutorials on linear analysis and the use of ppcov demonstrate how to construct parameter covariance matrices for use by PEST, as well as giving you some tips and tricks on how to apply this in practice with real-world data. The following few slides will cover some of the basics of implementing linear analysis in the PEST world. Just to note that PEST++ undertakes things in a slightly different and perhaps a bit more user-friendly manner. However, if you understand how to use PEST and the PEST utilities, it should be relatively easy to transfer that knowledge to using PEST++. If you are comfortable with Python, then I highly recommend you look into the PyEmu module, which provides an interface for PEST and PEST++, as well as implementing many of the same tools that we're going to discuss and which are available in the PEST suite. IEMU has functions that undertake all of the same things that we are going to discuss here. Again, the two tutorials linked on this slide demonstrate all of what is going to be discussed here with guided step-by-step instructions on how to do so. From the short exposition of the concepts and theory that we discussed above, it is clear that linear analysis depends on the existence of three matrices. These are the Jacobian matrix, which contains information on the impact of parameter changes on changes in observations. The prior parameter covariance, which contains information on the statistical distribution of parameters prior to history matching. And the covariance matrix of measurement noise, which contains information on the statistical distribution of noise in field measurements or observations. Practical implementation of linear analysis requires a pest control file from which the previously mentioned matrices can be calculated or to which they can be referred. All of the linear analysis tools that we're going to discuss here and which are discussed in the tutorials read these files, or this file. Ideally, linear analysis should be undertaken after a model has been calibrated. The values of parameters that are listed in the parameter data section of the pest control file on which linear analysis is based should therefore be those that were obtained during a previous calibration process. In a similar manner, the Jacobian matrix should be calculated using these parameters. However, if a model is truly linear, which it never is, the outcomes of linear analysis are actually independent of parameter, or would be independent of parameter values. Hence, even if a model has not been calibrated, then the use of a pest control file which features user-supplied prior mean parameter values should not invalidate the analysis, given its approximate nature. The parrep utility, which is part of the pest suite, can be used to adapt a pest control file or to update a pest control file from a parameter value file. So essentially taking the calibrated parameters and placing them as initial values in a pest control file. And prior to undertaking linear analysis, ideally one would update the pest control file with calibrated parameter values. Secondly, the linear analysis programs that we're going to discuss, or that we discuss below, assume that measurement weights listed in the observation data section of a pest control file are equal to the inverse of the standard deviation of noise, or the error, which is associated to the accompanying measurement. Again, there is a utility program in the pest suite named PWT ADJ2, which can update a pest control file in this manner based on the misfit model outputs with a calibrated parameter set. In this manner, so if each measurement weight is in fact the inverse of the standard deviation of measurement noise, then the objective function which is achieved through model calibration should be roughly equal to the number of observations which are used in the calibration. This is because every squared weighted residual is on average equal to unity. Lastly, assuming that the pest control file which was used for calibration includes regularization, it will contain a set of prior information equations and a regularization section. So to avoid confusion when undertaking linear analysis, the utility programs require that all of this prior information actually be removed. In this way, parameter values listed in the parameter data section of the file, along with the user-supplied prior covariance matrices, comprise the entirety of outside knowledge as it pertains to parameters. Again, as utilities, there is a utility named subreg1 supplied with pest, which just simply strips the regularization from a pest control file and creates another pest control file ready to be used for linear analysis. So some of the utility programs used for linear analysis calculate the uncertainty associated with a model's prediction, as well as quantities related thereto, such as the ability of various measurement subgroups to reduce the uncertainty of that prediction. The equations on which these calculations are based require the sensitivities to the prediction. So as I mentioned before, the Jacobian matrix must have been filled accounting for the sensitivities of a model prediction. Sensitivities of predictions to parameters can be extracted from a pest calculated Jacobian matrix if they are cited in a pest control file along with observations comprising the calibration dataset. If given a weight of 0 during calibration, these predictions have no effect on the inversion process or on the calibration. Therefore, before conducting linear analysis, predictions may be added to a pest control file that previously contained only calibration-relevant observations. This is convenient if predictions occur within the calibration timeframe, and if this is the case, then they probably pertain to sites and/or model output types that do not feature in the calibration process. Alternatively, again, as we mentioned before, if predictions of interest actually occur in the future or during a different period from the history matching period, then a special pest control file should be constructed in which the model is asked to simulate future conditions. You might refer to this pest control file as a predictive pest control file. This control file would list the same parameters as those in the calibration pest control file. However, observations that are listed are in fact model predictions. Their weights don't matter because they're not being used for calibration. This control file is simply used to construct a predictive Jacobian matrix. So to calculate the sensitivities of an individual prediction or even sets of predictions to changes in model parameters. A Jacobian matrix or GCO file can be obtained from a pest control file by setting the nopt_max variable to -2 in the control data section of this file and then running pest. Essentially, this instructs pest to calculate the Jacobian matrix and then stop and not try and improve the fit, for example. Again, as has been mentioned, this requires running the model at least one time for every available adjustable parameter in the calibration dataset or the pest control file. So along with the Jacobian matrix, we need to describe the prior parameter uncertainty. Prior parameter uncertainties are expressed through a covariance matrix, and there are several programs which we're going to discuss now that obtain this information required to build that matrix for you. And in the pest world, and this information is summarized or synthesized into a parameter uncertainty file, which the software then uses to construct the covariance matrix. If you wish to read up on the format of this type of files, check the part 2 of the pest manual. It's also described in the tutorials. Parameter uncertainty file is subdivided into blocks. Each block a block can be of one of two types, namely a standard deviation or a covariance matrix type. Standard deviations of individual parameters can be supplied in the first type of these blocks, and this is just done under the assumption that these parameters share no prior correlation with each other. So the standard deviation of individual parameters is supplied by the user. For cases in which parameters are correlated, such as spatially distributed parameters like pilot points, the statistical characterization of that group must be supplied through covariance matrix. Prior parameter correlation is often, but not always, an outcome of spatial proximity. Prior covariance matrices for pilot point parameters or other spatially distributed parameters can be built using the ppcov family of utility programs, along with their supporting programs which are listed on the screen. All of these programs belong to the PEST groundwater utility suite, and the tutorials which I've linked to previously on the ppcov provide you an introduction to how to use them and how to actually translate real-world information into prior covariance matrices for spatially distributed parameters. These essentially work on the idea of using a variogram to describe the geostatistical distribution of parameters through either space or time, and to create a covariance matrix. You can find a link to the link to the tutorial that describes this software is shown on the slide. So there are a suite of utility programs whose names begin with predunc, supplied with the PEST suite. Predunc stands for predictive uncertainty. And there are also members of a complementary suite of utilities that have names that begin with predvar, which actually explore parameter and predictive error rather than parameter and predictive uncertainty. Programs of these two suites can be run individually to accomplish specific tasks. So these tasks can be tailored to the particular context in which the modeling is being applied. Or alternatively, there is a program named genlinpred, which can be used to run many or all of these programs in sequence to undertake a default set of tasks. And in practice, it's usually easier to simply use that in most contexts. And you'll see that in the tutorial that you're actually using a version of genlinpred rather than the individual predunc and predvar utilities themselves. So as I've said before, linear analysis tasks in general aim to assess prior prediction probability, posterior prediction, and parameter probability, as well as assess data worth. To assess prior and posterior parameter uncertainties, we use the predunc7 utility. Predunc7 reads a pest control file and a JCO, so a Jacobian matrix file, as well as the user-prepared prior parameter uncertainty file, which we described earlier. From those three files, Predunk7 obtains the matrices which we have described. It then writes a posterior parameter uncertainty file. Well, effectively it writes a posterior parameter covariance matrix. A series of other small utilities can be used to extract the posterior parameter variance from this matrix. Once you have both the prior and the posterior parameters uncertainties, then their ratios as well as other informative quantities can be readily calculated and plotted. It's often quite informative to display these ratios of relative uncertainty reductions. As in particular for spatially distributed parameters, it can be quite informative to see where in fact the history matching process has reduced uncertainty and where it has not. And often this provides some insights which you might not expect. Predunk1 calculates what we're probably most interested in, which are the prior and posterior predictive uncertainties. So this is effectively the uncertainty around a observation, which is your prediction, which you might then display as something like that. Predunk4 calculates the contributions made to the uncertainty of a particular prediction by single parameters or by groups of parameters. This can be informative when considering whether simplifications that are embodied in a model's design degrade its performance. If parameters that are associated with some worrisome aspect of a model's construction contribute in only a minor way to the uncertainty of decision-critical model prediction, then approximations and simplifications associated with that model feature are relatively harmless as far as that particular prediction is concerned. There is actually a GMDSI worked example which illustrates the use of linear analysis to explore the effect of model defects, in particular in terms of the choice of boundary conditions and boundary condition values on affecting a model prediction. Finally, perhaps one of the most useful outcomes of linear analysis is undertaken by Predunk5, which evaluates data worth. Data worth increases in proportion to the ability to reduce the uncertainties of one or more decision-critical model predictions. Once the uncertainty of a prediction has been calculated based on existing current data, it's a simple matter to calculate what that uncertainty would be if certain items of data were either removed from the calibration dataset or added to that calibration dataset. Now, because the values of neither measurements or parameters actually appear in the equations used to assess this uncertainty, the ability or otherwise of an enhanced calibration dataset with more data to reduce the uncertainty of a decision-critical prediction can be rapidly assessed without actually acquiring that new data, nor even having to guess what values that those observations might have. This makes it an extremely useful tool to prioritize what new data to go and collect to reduce the uncertainty of a given model prediction. Now, this tool doesn't let us know what the prediction might be if we collect that new data, but it does give us an indication of the relative data worth of new observations. So we can prioritize which new data to go and collect, which should maximize the reduction in uncertainty of our model predictions. In contrast to linear uncertainty analysis, non-linear methods do not suffer from the limitation of assuming a linear relationship between model predictions and model parameters. Given that such relationships are rarely linear, this is actually an important consideration. Nevertheless, non-linear methods are not free of assumptions. These include those associated with the conceptual model on which the numerical model is based, and those associated with the prior parameter probability distributions. Of particular importance is the potential for high permeabilities to exhibit different patterns from those exhibited by the low permeabilities, and for regions of high permeability to exhibit greater connectedness than regions of low permeability. Think fractures and karst networks and so on. Unfortunately, the effects of this and other types of geologically realistic hydraulic property dispositions are difficult to include in either linear or nonlinear uncertainty analysis. Nonlinear methods can also sometimes incur a higher implementation cost than linear methods and do not facilitate the calculation of value-added quantities such as data worth. That being said, under some circumstances, nonlinear uncertainty analysis based on the iterative ensemble smoother implemented in PEST++ IES can be numerically cheaper to implement than linear uncertainty analysis, or as you will see when you undertake the tutorial. The PEST++ IES iterative ensemble smoother is a member of the PEST++ suite. Just like PEST, it employs the same non-intrusive model interface. It reads the same pest control file with a few added variables to control the action of the iterative ensemble smoother. IES samples the posterior parameter probability distribution. It commences by using a suite of random parameter fields sampled from the prior probability distribution, so illustrated by this red histogram on the slide. Each parameter field is referred to as a realization. The set of all of realizations is referred to as an ensemble. Then, using an iterative procedure, IES modifies the parameters that comprise each realization so that each is better able to reflect the historical data. So in other words, IES adjusts the parameter of each realization in order to reduce the misfit between simulated and observed and measured observation values. The outcome of this adjustment process is an ensemble of parameter fields, all of which allow the model to adequately represent observed system behavior. These parameter fields can be considered samples of the posterior parameter probability distribution. By making a prediction using all of the members of the ensemble, the posterior probability distribution of that prediction is sampled. A particularly attractive feature of the ensemble smoothing process is the model run burden of parameter adjustment is not related to the number of parameters that are adjusted through this process. Instead, it is proportional to the number of parameter realizations that are adjusted, so however many realities we have generated. During each iteration of its adjustment process, S++ IES first undertakes as many model runs as there are realizations. From the outcomes of these runs, it calculates a rank-deficient approximation to a Jacobian matrix. It then uses this matrix to improve all of the realizations. In theory, the number of realizations that are required for implementation of this process need only be as great as the dimensionality of the solution space, which is often no more than a few hundred or even less, regardless of the number of parameters that comprise each realization. In practice, we'll usually use a few more just to get a better fit between model outputs and field measurements. And it's also good to have a few extra realizations on hand because often there will be a lot of model failure during this process, and we might need to replace some of the realizations which dropped out along the way. Prior parameter probability distributions are provided to PEST++ IES in the same manner as they are for the linear analysis methods which we described beforehand. So essentially a covariance matrix of prior parameter probability. This prior parameter probability covariance matrix is used to describe the parameter probability distribution, which is then sampled or randomly sampled to provide initial parameter values for PEST++ IES. It's not necessary that all of these initial parameter sets be completely random. In fact, it's often advantageous for at least one of them, or for one of them to be comprised of the prior parameter means. This realization is referred to as the base realization in PEST++ IES, and the adjusted base realization is often a reasonably good approximation to the parameter field of minimum error variance, which we achieve through conventional calibration. Once samples of the posterior parameter probability distribution have been obtained, they can be used to make any prediction required of a model. There are occasions where it may be worthwhile to undertake conventional model calibration before using PEST++ IES. This, of course, incurs a lot higher numerical costs, especially if the model has many parameters, as we need to fill a Jacobian matrix. Nevertheless, it may be worth this cost in some circumstances for the following reasons. The use of a full-rank Jacobian matrix, which one obtains through calibration, can often afford a better fit than using a rank-deficient Jacobian matrix, which is obtained with IES. This will usually be the case where there are many measurements, and thus the solution space is actually quite large. It is important to note, however, that obtaining a really good fit between model outputs and field measurements should not always be the highest priority for a history matching process. However, it sometimes might be important where details of temporal or spatial nuances of the calibration dataset are quite rich in some prediction pertinent information. Secondly, the full rank Jacobian matrix obtained as a byproduct of classical or traditional calibration provides a really sound basis for linear analysis. And as we explained before, this can provide us insights that are otherwise difficult to obtain. Thirdly, in particularly difficult history matching contexts, IES might perform better if the initial ensemble is actually centered on a calibrated parameter field, so centered on the parameter field of minimum error variance, and or if the sample is based on samples of a linear approximation to the posterior parameter probability distribution, which we'll discuss in the next couple of slides. Finally, history matching based on a full-rank Jacobian matrix can often provide a more geologically plausible picture of the heterogeneity that must exist than can be obtained in other way. So these are some of the reasons why you might want to calibrate first and then implement IES, although not all cases require them. So we'll now discuss a couple of workflows through which to undertake posterior uncertainty analysis following a conventional model calibration. So ideally, conventional calibration yields a parameter field that lies somewhere near the center of the posterior parameter probability distribution. So we start with our prior and our prior mean. We calibrate, we obtain a posterior mean, which is our parameter set of minimum error variance. Initial parameter realizations for the use of PEST ++ IES can then be generated by sampling the probability distribution that is centered on the calibrated parameter, illustrated by the blue line there, but that employ a prior covariance matrix. So still assuming that wider or larger prior uncertainty. Experience shows that PEST IES can then, or PEST ++ IES can then rapidly adjust these samples until they fit the calibration dataset well, and will often retain nuances of model to measurement fit, which were attained during or which were discovered during the preceding calibration process. So effectively we end up with after IES has improved the fit of the sampled realizations, the posterior probability distribution will then be much thinner. Second option is a variant of the first. So once a model has been calibrated, a modeler might use finite parameter differences, so traditional calibration, to fill a Jacobian matrix, as we discussed before, much as one would have done in order to apply linear analysis tools. This, of course, can be an expensive exercise, requiring as many model runs as there are adjustable parameters. Once this is done, the linear analysis tool Pridanker 7 can be used to construct a posterior parameter covariance matrix. So we have a linear approximation to the posterior parameter distribution, which is based on this covariance matrix and the calibrated parameter field. This posterior parameter probability distribution can then be sampled by IES. So effectively, IES is already starting from samples which are quite good approximation to the posterior parameter probability distribution, and adjustment of the parameter realization should be relatively fast in order to fit the calibration dataset well. And often this reduces the number of iterations that IES needs to undertake. So just a reminder, there is also a tutorial on how to use PEST ++ IES, which takes you through the three different options of using IES directly or calibrating first, and describes step-by-step everything that I've just discussed now, as well as providing a lot more detail on actually how to interpret the outcomes of using IES. Lastly, I'm going to discuss something which you don't see applied very often, but which is a slightly different way of addressing uncertainty in terms of model predicted outcomes. Now, the integrity of prior or posterior predictive uncertainty analysis depends on the integrity of the prior parameter probability distribution. Because geological media are complex and because numerical models are necessarily upscaled representations of reality, random parameter sets that sample an off-the-shelf probability distribution, such as a multi-Gaussian probability distribution, are quite unlikely to actually be geologically realistic, or whatever that actually means in an upscaled model domain. They are likely to emit patterns of connected permeability or connected impermeability that can profoundly affect the movement of water and contaminants through the subsurface. An added problem is that all of the methods discussed above, through which samples of a prior probability distribution can be morphed into samples of posterior parameter probability distribution, have difficulty in maintaining connected permeability during this morphing process. In fact, the theory behind all of them actually assumes a multi-Gaussian parameter probability distribution, which does not account for that type of connectivity. Failure to include these geologically reasonable patterns of connected impermeability or permeability in random parameter fields of either the prior or the posterior can easily result in the underestimation of predictive uncertainty. And of course, the outcome of this is that you can result in the underestimation of the risks associated with contemplated courses of management action. This problem can be overcome through direct predictive hypothesis testing. The workflow is broadly as follows. First, one calibrates the model to obtain a parameter field of minimum error variance, and thus the parameter field which displays the heterogeneity that must exist to explain the calibration data set, usually the simplest heterogeneity required to explain the data. If appropriate at this stage, one might revisit the characterization of the formal or informal characterization of what subsurface heterogeneity should look like. So you might revisit the variogram with which you believe best explains geological heterogeneity and so on. And you might also reassess how well the model can be expected to fit the calibration data set. So what is the minimum objective function that you can actually achieve given the model to measurement misfits from a calibration process? We would then consider the prediction of management interest, normally something that can adopt a range of values, but that management of the groundwater, or some of which management of the groundwater system seeks to avoid. So, for example, on the screen, that predicted value, we do not want it to drop below the star. In direct hypothesis testing, one would then recalibrate this model, starting from the calibrated parameter field, but now including that unwanted value of the prediction as part of the calibration dataset. The idea here being that one must both fit historical data, but also observe that that bad thing will happen. The outcome of this is to discover whether it's possible to have both historical data being well represented, as well as this prediction of the negative thing that we don't want to happen happening. If that occurs, then we cannot reject the hypothesis that a bad thing will happen due to our management action. If the outcome of this calibration results in a parameter field that's still reasonable, that looks geologically defensible, and if fit between the model outputs and measurements of historical system behavior still appear to be credible as well, then, as I said, the hypothesis of the unwanted prediction, that the unwanted prediction can occur, cannot be rejected. Now, in practice, in groundwater modeling, search for uncertainty and you will find. In practice, it's almost always possible to achieve a case in which the bad thing will happen. So PEST will search for any possible combination of parameters in which the bad thing will happen. However, an outcome of this is that you will find what parameter or what conditions or what parameter values have to exist in order for the bad thing to happen, which can be useful to then explore what new data you need to go and collect or what new observations you need to collect to start to reject this hypothesis. Direct hypothesis testing does not require any specialist software beyond PEST. However, it does require efficient implementation of highly parameterized inversion. So you need to have a suitably high number of parameters to support the emergence of potential connected permeability, if this is required for a hypothesized prediction. And so you also want your system to be extremely numerically efficient, as the simulation time might span you have to simulate both the past and the future in one single model run. So there is a mode in PEST and some of the PEST variants called Pareto mode, which is a mode that aims to facilitate predictive hypothesis testing. This mode recognizes the somewhat subjective nature of a model's decision or a modeler's decision to reject or not reject a hypothesis of management interest. It's not a very efficient process, but it can be implemented. And as I said, it's not very often that you see this method applied in practice. So with that, we come to the end of this talk or this video. Just to wrap up, or to provide a bit of a summary, we've gone over three general methods to address uncertainty in groundwater modeling in the context of decision support. There are a few others, but I haven't gone into them due to a matter of time and just to stick to the most perhaps widely used or commonly used methods. As we've seen, linear analysis provides a very cheap approximation of both parameter and prediction uncertainty. Although approximate, those assessments of uncertainty are usually good enough for a decision support context. They have the underutilized added benefit of data worth, so particularly useful to explore what additional data to collect in order to reduce uncertainty. We then went into nonlinear analysis or nonlinear uncertainty analysis methods. Again, in the past, others were used, but in the last few years, ensemble methods, and in particular the iterative ensemble smoother implemented in PEST++ IES, have pretty much superseded most of the other nonlinear analysis tools that are easily available and are the go-to tool at the moment. They offer quite cheap or computationally cheap methods of assimilating data and assessing the nonlinear uncertainty in terms of parameters and predictions. And lastly, we touched very briefly on direct hypothesis testing, which, as I said, is not very commonly implemented, mostly because I think it's a bit too challenging to do well. However, it is the most scientifically robust approach to actually assessing uncertainty in a groundwater modeling context. So I think, or perhaps one of the other reasons why it's not used so much is that you will pretty much always find that your bad thing will happen, or that there is some way that your bad thing will happen, although it can be used to identify the conditions which must exist in order for the bad thing to happen, which can then be used to prioritize what data to collect and what observations to go and measure to see if it is possible. As I said in the beginning, this video shouldn't be taken on its own. You should go and complete the series of tutorials which are on the GMDSI website. They will ground a lot of the perhaps nebulous information and wall of information that I've just given you, and help you to associate these concepts to how to actually apply them in the real world. You'll find that it's not half as complicated as it might have sounded. And these tutorials will take you step by step and hold your hand along the way, showing you exactly what you need to do and how to think about it and how to interpret the outcomes. Finally, there's one very important aspect of decision support modeling which we have hinted at but never really gone into in depth, but it is fulcral to designing and actually implementing everything that we've talked about here in terms of model calibration and uncertainty analysis, and that is the degree of model complexity. In the interest of time, I'm not going to go into it here, and also because John and Catherine have prepared extremely good material explaining these concepts, which are encapsulated in the webinar, which you can find through the link, as well as in a document that describes all of the ideas and the concepts behind, which are discussed in the video, which you can find in the monograph sections of the GMDSI website. If you have any intention of becoming a groundwater modeler, then you should definitely watch and read these things and incorporate them into how you think about designing models into the future. The concepts therein are fundamental to be able to design models for data assimilation and to be useful in a decision support context. And that's it from me. So I hope that was useful for you. And again, please do go and do the tutorials. I'm sure you'll find them useful, and perhaps even more useful than this video. And that's all from me. Cheers.